Good morning. So I'm teaching this course on advanced integrated circuits soon, and in that course we have a project that is design a temperature sensor. So I've been thinking about how to make it easy to start, and I have this idea I kind of want to try. Let's see. I'm not sure it's gonna work because maybe it doesn't have a great temperature coefficient, but I want to check and see if it does. And I thought I'd just walk you through the design steps. So this is just, I guess it's more a show and tell type of video. So I don't have anything right now. I'm just in my ASICs repository with all the IPs. So you can watch a tutorial if you want to know how to make a example, or go through the tutorial. Anyway, CIC conf new IP group example, and Janeway let's get schematic editor up and running, and let's see, what do I need? I definitely need a reset 1v8, and I need a output, and that needs to be an open. And I kind of want to encourage the students to actually make sub-circuits of their stuff. But let's see, what do I need here? So the circuit I have, I should probably take a picture. Maybe, let's see. Okay, it's probably better to show it like this. So just a picture of the paper I showed. So the thinking is, I don't want to create a full band gap and stuff like that yet. I want something quite simple that seems to give some sort of temperature dependent behavior. So the idea is, if I take a resistor connected to VDD through a PMOS, this would need to be connected to the power up to turn it on, and put that into a NMOS, mirror that current, and then put that current into a capacitor charging down from VDD. Then at some point that should turn off, and that should be related to the VGS of this transistor. And that's going to turn off at well, the VGS of the transistor is going to go down with frequency. Sorry, not with frequency, with temperature. Just forget about the stuff here. And then the current's going to go up with temperature. So it might actually be that these two compensate each other. I'm not sure. I spent about 1 minute thinking about this. So what I want to do now is check. But I do want to encourage the students to sort of split their design up a bit. So this kind of had two components. We have a current that is somehow related to temperature. And then there is a sort of conversion from the current into a time. So let's split that up into two circuits. So let's make a new one. What did I want to do here? This would be my current mirror. So I want to add a transistor. But now I want to add a transistor of the correct size. So let's first figure out how big the PMOS should be. So I have this transistor library. You can see that in tutorial. I'll paste the link in the description below. But I kind of want sort of a current of not that many microamps. So actually it looks like even the small one, the 2C5F, that's quite a bit of current, about 10 microamp. But okay, let's go for a 10 microamp current. That will give me a GM or ID of roughly 10. So I need a 2C5F0. So let's see, let's find that. 2C5F0 for the NMOS. And let's place that, flip that. That was Shift F, if you didn't know. And then wire that up. Oh. Now I'm just pressing W. And let's do it like that. And then I need to connect the gate to the drain on the NMOS side, or the input side, and this will be by output current. And I need a resistor. So let's think about that. First of all, let's find the resistor. That's going to be in here. It's probably, let's just pick, is it that one? No, this one. Okay. And now we need to figure out how big that resistor should be. So I kind of want, what did I say, about 10 microamps? Sorry. Let's first save this one. Save. Oh, untitled. I want to save as. And we want to save it to the design directory here, there. And let's make sure that it has a unique name, you and me. And then, what should we call this? This is the temperature to current, TI. And let's find a, actually let's just copy from here. Well, we want that one. Okay, so this will be my supply. And let's see, what was the VGS of this transistor? So the VGS is around 640 millivolts. Let's jump to the terminal. Python 3, let's see. So we have 1.8 volts minus 0.64. And then I want 10 microamps. So I need about 116 ohms. So 116 kilo ohms. And let's figure out how big this is. Yes. So this is 16. So 16 times 7535. 7535 times 16. Oh, so that's about right. Okay, let's keep it like that. Perfect. Okay, good. I need a VSS. And, oh, I forgot. Yeah, let's put that in afterwards. And I want a output pin. And I want this to be called, it's not a bias current, but it's an I current, IPT proportional to temperature N, because it comes from an NMOS. Like that. And then I forgot a PMOS up here to turn this thing off. So we kind of want, there I don't really care that much. I just want it to be big enough. So if I pick that one, it should be, let's see, no, let's do that one. Let's just make sure that that PMOS, when the, yeah, 30 microamps when it's GMIDO 10. That's fine. Let's put that in there. Okay. And then I also kind of want to turn this current mirror off. So let's do that with a similar transistor. In this case, we don't really need the long one. We can use a short one. It doesn't really matter, actually. They're the same size, so let's just keep it like that. And then connect that to VSS. And let's see, this needs to be, so I want this to be powered. So this needs to be power up N. Like that. And then, what about this one? So here I want it to be on when power up is high. That means it needs to be connected to the same signal. So actually, let's just put this like that. maybe a bit lower. Okay, so now I have my current mirror. And let's just add a border to make it pretty. Like that. Move it to the middle maybe. Okay. And then I want to make my symbol. Make symbol from schematic. Yes. And let's open that up. Let's see if it looks roughly how we want it. That one. Yeah, that's fine. It's not that important. Actually, kind of is. It's important to make pretty schematics, but in this case, it's relatively simple. So let's just leave it like it. Actually, no. Let's make it pretty. It's worth spending a bit of time on it. Okay. First of all, we should make sure that VDD is up there. VSS down here somewhere. Power up. That's an input signal. It should be on this side. Oh. Let's see, VSS, power up. Let's get that to... I'm pressing the M button, by the way, now to move stuff. And like that. And let's just put it out here. Okay. And now L maybe? Is it that line? Yeah. Line. No. Line. There. 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 And there. And then what we actually have here is a current, right? So in these kind of symbols, I kind of like them to represent kind of what's inside. Let's like that. So that looks like a current. Maybe we should add a line there too. Like that. And then if I do like this, and then you kind of understand what's going on here. But that's wrong. I notice now. Okay. Because this current is going the other way. Okay, let's fix that. So this current is actually going down. Like that. And that means we probably should move this one a bit further up. Like that. And then now it should be a bit better. Let's move that over to VSS. Oh. Like that. And then let's put a switch in. And then let's move that power up. Oh, wait. Now I have to be quite careful. I changed the grid. So we should make sure that these align. Like that. Okay. So now it's sort of, we can see what this is. It's a current. And it goes down. So it doesn't really represent the circuit inside, but at least we explain what it does. And that's kind of the point of schematics. It's to give you a very quick understanding of the circuit. Okay, we need... So here we have power up N. We need then the inverted. So let's find an inverter. It's going to be a transistor library. It's called IVX. We don't need this particular size. It doesn't need to be particularly quick. It just needs to invert. Like that. And then there. And then let's put these in. So actually, I kind of like Shift I to find the lab wire. What I was going to say was I kind of like connection by name for powers. It just makes maybe a bit sort of cleaner schematics. So VDD 1V8. You have to be a bit careful though, because it's quite easy to do a typo, like I almost did there. VSS. That's what I call the part. Yeah, that is. Okay, then we have that one, and then I need to copy this one and hook it up to my circuit. Okay, now we have that. Let's call it something too. X, what's TI? Okay, and let's look at our circuit again. Now I need the reset and this, okay? So let's make a new schematic, and in here, what do I need? I need a reset switch. That's going to be a PMOS. Size doesn't actually, let's pick it a longer one. And that needs to be connected to VDD. So let's just copy VDD from somewhere. There we go. That one. And what else? We need a capacitor. So actually, I chose 10 microamps. So now I need to figure out how big my capacitor is. So let's say the change in voltage is going to be, actually it's going to be around this. That's going to be my voltage change. And let's say I want to make that happen in a microsecond. And then, actually that's going to be 1 over that, I think. And then, let's look at the equation. So we have I equals C dV/dt. So the change in voltage divided by the time. That's what I have there now. Because what I want is the capacitance. So it's going to be I divided by that. So that means I need 10 E minus 6. Oh, that's a big capacitor. 8 picofarads. Ooh, ooh. Maybe I have a slightly too high current. Let's make it smaller. Let's make it 5 microamps. Still large. 2.5? Okay, 1. That's more a picofarad. Okay. So I need a picofarad capacitor. And I need to make my current smaller. So let's see, cap 4x. Let's take this one then. And figure out how large that is. Okay, so that's 4 of those. So it's 53.4. No, 53.8. No, that's 15. Okay, so I need 16, but that was 4 of them. So I need 4 of the big ones. So I need 4 of these. 4, 3 divided by 0, 3, 0. That should be correct. Okay. So I'm going to reset that. And actually, no, that should be fine. Should be able to reset it quite quickly. So that's, if I have a reset that is high, when I want to reset, then this needs to be reset N, right? Because it wants to be on when the reset is high. Okay. And then I need my current, what I call it. And actually, let's save this symbol before I manage to screw it up. Let's see. Janeway. This is current to digital. ITD. What is this? VSS? No, that was my current. Let's see. Cancel. What did I call my current? IPTN. Okay, so that's going to go straight into my capacitor. Like that. And then my thinking was, what was my thinking? That I just put that into an NMOS. And let's make that, actually just use the same size. Like that. And what did I put here? Here I put just a resistor. Why did I put a resistor? Because I only wanted to be determined by a, I don't know why. It's kind of like an amplifier, right? So why didn't I want to use an inverter there? Maybe I wanted to limit the current. I don't know. Okay, but let's put put in the resistor. Where did the window go? Let's just pick the same one. It's a bit big maybe, but anyway. Okay, and then I don't want an inverter. And maybe this needs to drive something. Let's make it a big one. Bigger one. Put that in there and there. Okay, so let's have a quick look at what happens to the circuit when we're off. So the current's going to be completely off when we're in power off. So maybe we should have another transistor for the power off. And that can have the same function actually as so when the power up is low, then I want to enable this one. Okay, and then I'm going to add an O pin. Let's switch that symbol first. Let's power B. Let's see, what do we want here? We want DO, digital output. Okay. And then I kind of want to make a pulse that is 1 when my reset is active. Let me think about that. Actually, let's open Emacs so you can see what I'm thinking. And let's make it bigger. Okay, so when reset is 1, no, right. So reset, we have our signal, reset, we have power up, and we have, what should we call it? Pulse. Pulse. So reset is 1, and power up, no, actually, not power up. I want, yeah, that's power up. So this is me thinking. It's back and forward. Okay, so we have reset 1, power up is 1. Then DO should be, let's assume it's 0. Then I want my pulse to be high. No, then I want my pulse to be low. When reset is 0, and power up is 1, and my output is 0, then I want my pulse to be 1. But when reset is 0, my power up is 1, and DO is 1, then maybe let's skip the power up thing here. What I want then? I want 0. Okay, so let's complete it. 1, 1. What do I want here? 1, 1. I'm just trying to work out the digital gate here. So if I do like that and rearrange it down here, okay, what does that look like? That looks like a NAND if I do that. Yeah, that's a NAND. Okay, not AND. I need that one. So then, do I want the digital output at all? Yeah, let's keep it there for reference. We can figure out the delay and stuff on the circuit. Okay, so let's see. We want that one, and I wanted reset, I believe. So reset B1V8. I'm writing B because I'm going to buffer it on the top level. And in this case, there's not much circuit, so let's just hook up these things here. And I think we still need a ground. Like that. Okay. Let's move that a bit. Like that. Let's see. Okay. Pulse 1V8. Okay. Good. What else? A border. Yeah. Let's put it into the middle. And let's make the symbol. And let's open it up. Let's make it a bit bigger. And let's group these elements together. So you might be wondering why I have 2 reset here now, and why not put the inverter inside? Well, I already have the inverter on the top level, so I don't need to generate the signals again. And let's see. So let's also look at what the function here is. How do I communicate? In a nice way, what happens in this symbol? I don't actually know. I could draw the circuit, but you can go inside and see. So it's no point in drawing the circuit again, kinda. Yeah, so let's skip it for now. Let's see if I think about, well, or get an idea for how I want to draw the symbol. Let's see. Okay, so VO, that's actually going to be named DO. DO 188. I like to postfix my digital signals with a voltage. And that is to make sure that when I do dual rail designs, like 3 volt or whatever, 3 volt and 1.8 volts, then I make sure that I don't hook up, well, I try to make sure that I don't hook up my 1.8 volt supply to, or my 3 volt supply to 1.8 volt logic gates. That's a very bad idea. And promise me, I promise you that happens. Okay, so what did I want to do here? I need a power up buffered. Now, this may seem a bit stupid, but I don't want to use my input signal, the power up here, directly. And the reason for that is quite often that can come from far away. It can come from a driver that is very far away and maybe on a slightly different supply. So you kind of want something to increase the voltage before you put it into at least transistors. So I like to have at least an inverter or something like that to make it, to regenerate the signal levels. So that one's the buffered. I'm just looking at my symbol here, and I don't really like how it's organized. So let's see if we can. So we kind of want the current. Where's the current? Am I happy with that? That kind of works. And then we can do the reset on top there. Oh, let's copy it when we get like that. Okay. Let's see. So that's the buffered. And now, yeah, if I go there, it's not going to be the prettiest thing. But that's okay. And the buffered one is going to go there. Okay. That, I believe, is my full circuit. Now we want to simulate this thing. And do I want a state machine for it? Digital? So what do I need? I need my reset and a power up. Nah, I can do that with something simple right now. But should I do that? Let's do that first. Let's see. Let's go to the simulation directory and make. Oh, I never remember the command to make a new cell. Where did I have that? Make files. Sim make. What is it? Make cell. Okay. And I actually want the top level, so that should be fine to just do that. Okay. Now we need to open up the test bench. Let's see, where did I go? I want my sim, and I want my transient. So I need to do what? Power up's gonna go on, that's fine. And then I need my power up. And that can stay lower for, let's say, a microsecond. Ah, I just remembered something. Okay. And then at 1.1 microsecond, it can go to VDD. And then I'm going to keep my reset high for a little bit longer. So that's actually going to start out at AVDD. And then at 1 microsecond, actually, let's say that's 2 microsecond, it's going to stay high and then go low. Okay. What else? I think that's kind of it. Do I need anything else? Yeah, I need to save, but saving all here, so that's okay. Let's see what happens. I need to go into the Janeway. Like that. Now, these commands, they write the netlist for me and blah, blah, blah. So let's see. Okay, we at least got a simulation running. And let's have a look at the results. So we want to see... Oh, that doesn't look good. Why? Why is that foobar? Or is it? Okay, now we need to name things. So this IPTN node, let's name that. We need that wire label. Where is it? Lab pin, lab wire. IPTN. And let's see, we kind of want to... Oh, I forgot one thing here. Here we should have... Yeah, we're going to place it. It's going to be a subthreshold. Okay, fine. Let's make a subthreshold mirror then. So that's 9,0. That's 10 devices, and that's 1. Yeah. Okay. It's not ideal. It's a subthreshold current mirror. We should really make that cap really much bigger, but fine. What else? No, I wanted to name things. Name. Why do I want to name things? Well, I want to be able to find them in a simulator. I don't want to spend time on... So, this is a VBIAS node. Let's call it VBN. That's ground, that's fine. And let's have a look in here if there's any nodes I want to name. Yep, that one. Let's just call that VO. Okay. And like that. And let's just run the simulation again to get those new names in. And reload. Okay, so what do I want to look at? I want to look at the IPTN node. Ah! Now, this simulation is only running for 10 nanoseconds. That's why. I need to run for, let's say 5 microseconds. See if that's maybe not that fine stepping. So that's why it looked weird. It hadn't booted up yet. Okay, reload. Okay, now this is actually looking pretty good. Okay, let's have a look here. So what happens? Time we can delete. At when we turn on the reset, there's a small charge injection on the cap. Let's ignore that for now. And then we see a pretty linear curve until it gets down here and it flips. Now the interesting thing is, how does this behave with temperature? So let's just make sure that our pulse signal, so if we have our reset, okay, so that's going down there. Wait a minute, digital output is high. Wait, did I? Okay, so that's going from low to high. Yes, of course it is. Ah, so that means my pulse is probably not correct. Let's see, pulse. Well, let's add a new axis so we can see. Yeah, that's pulse is wrong. Okay, let's fix that. Let's just add another inverter. And then hopefully our pulse will be correct. Let's see. Reload. Wait, what? Let's delete the signals here. VO. Okay, so reset is low. ZO is low. 0, 0. Oh, is it an OR? Not OR. Yeah, it is. It's me that, okay. These are the things that I usually don't think through that well. I probably should, but I don't. Maybe it wastes me a bit of time, but I get it right in the end. There we go. Now I have a pulse. Now, the reason I wanted a pulse is I should be able to measure the duration of this pulse. So in my measurement file, let's see if I can figure out how to do that. Not really without getting the ngSpice manual. I should have it on my computer somewhere, I hope. Or just get that one. Okay, so table of contents. Now we want measurement functions. Where are they? I never remember this. Initial conditions, no. Measurements after AC. Okay, dot measure. Here we go. Okay, so what do I want? I want the duration, measure duration of that pulse. Most skip there. Let's see. Trig. So this looks promising. So minus tran tdiff tpulse trigger on voltage. Which voltage? Pulse 1v8, value 0.9, rise 1, voltage 2, it's pulse 1v8, val 0.9, fall 1. Okay, let's see if that gives us what we want. Okay, so here it says, is it 800 nanoseconds? Yeah, it is, right? Yeah, 800 nanoseconds. Let's just make sure that it actually, that looks sensible. Okay. Yeah, it kind of looks like 800. Yep, it is. Good. Okay. What do we want to do then? Now we want to sweep over temperature. Okay, I know I've done that somewhere in the Janeway. Was it here? Sim. Did I do it in Spy? Let's check. Yep. This looks like promising. Okay, let's just copy that thing. Let's go to the transpy. So what we want to do now is sweep the temperature. So from temperatures, let's go minus 40, minus 20, 0, 20, 60, 80, 100, 125. No point in going. Let's actually stop at 100. Let's see. We want to skip this old stuff here. Let's use the same thing as before. 10 nano, 5 micro, and then it's going to write the, yep, that's okay. So that's going to simulate 1, 2, 3, 4, 5, 6 temperatures. And let's just copy this one to the measurement file. And let's, for each of the circuits, let's see. So let's actually take this one and load. And then we can, for each of the temperatures, we can set the name to that temperature. I'm not going to go through the details here. Let's see if that works. It took a bit of time to simulate. I could probably make it faster. Let's have a look. Minus 40 volt. Let's get the pulse. I should probably, that doesn't look promising. Yeah, that's what I suspected. I think maybe, yeah, these compensate each other. That's too bad. Let's look at the VO, and I'll explain what happens. Now let's TN, IPTN. Okay, let's VO there, and let's get the VO here. That's the PTN. So those look, actually those look too similar. What's a VBN? Let's open up a high temp one. Okay, so that's difference in VBN at least, and IPTN. There's a very slight difference in current. That's a bit surprising. Okay, so there is a difference here, but it's very minor. Okay, so what we made here is a pretty bad temperature sensor. We can see that at low temperatures, actually, let's sorry, I'm just thinking of it. Yeah, let's write a quick Python program here. So what I want to do is I want to plot this thing. And we want the f name. That's going to be, let's just, it's not going to be the prettiest code, but let's get the first argument. And then what I want to do is, actually, I'm going to assume that there's a file. Actually, that's going to be the YAML file. With open YAML safe load v, and that's gonna into object, and then for u in object if research t, what did we call it? T pulse. If not, then continue. And let's see. So then my I'm gonna split that. Actually, we don't need just split. Like that, and that's gonna be t. Don't care actually. Don't care. And temperature. And then I'm going to create a dictionary on dict temps. So temps temp equals objects O, like that. And then I want to plot temps values, no, keys, temp values. Is this going to work? first time right. Not gonna happen. Yeah. Yeah. Where did that go? All right. Float. I think. No? Okay. Oh. No. Let's just print temps and see what's in there. Alright, yeah. I kind of want that to be a float also. No? Int? Why? Maybe I need to do this. Come on. Oh, right. This one. And that one. It's functions, not properties. Okay, good. And then let's do line style. None. Marker. O. Marker size 5. Marker. Can't type. Okay. Yeah. So we made something where the delay changes oh so slightly with temperature, but it's not very good. It's actually pretty bad. So I think part of the reason for that is whatever change we have in the voltage is quite small. But anyway, actually I'm going to stop here because you can figure out how to improve it. You can figure out how to change or maybe modify the circuit, and it'll get you going. I'll put the link to the repository in the description below, and you can play with it. But this is how I'd like my students to draw their schematics, and it seems to work. It's just that the current that we get is pretty bad, and our trigger threshold, I would assume that's partly the reason also. Let's have a look at that. So if I take the minus 40 and let's look at the, what is the called, what did I call it? IPTN. IPTN for that one, and I want the minus 41. Those are also slightly different. And then look at the VO to see when they trigger. We can see that, yeah, they trigger at slightly different times. Which one's the green one now? So the green one triggers there, and the red one triggers there. Okay, so that's not too bad. Yep. But this small change in delay, what is it? Well, it doesn't really change at low temps, but from 20 degrees to 90 degrees, it's only a few nanoseconds, so not very major. So you need to make a current that is more temperature dependent, or a threshold maybe that is constant, like yeah, I don't know. You'll figure something out. But I wanted just to demonstrate how my thinking goes when I go from a few minutes on a piece of paper to now almost an hour, I guess, on trying to see, did the idea work? And although the principle does work, there's still quite a bit left to get it into something that has a reasonable temperature or measurable temperature change. Yeah. So, but have fun. I'm going to stop there. I'm going to put the description in the link below and so on. See you later.